Alright, part A, draw a free body diagram showing all forces acting on the car and draw any arrows indicating the direction of acceleration. Okay, so that's the cone. Half angle will be theta right there. Car will be about right there. This height will be defined as h. I'm not going to draw the arrows representing the motion of the car here just to make it easier for us to see the forces acting on the car. Of course, there's going to be FG, points straight down, always points straight down in any system no matter what. There's going to be FN from the inside surface of the cone acting on the car as well, always perpendicular to the surface like that. And then the direction for the acceleration of the cone will follow the direction of the centripetal force acting on the cone, which always points in the center of the circular shape that the object's motion is making. So that will be A, C for centripetal. Again, pointing towards the center. Now, part B, in terms of given quantities, derive an expression for the normal force. Okay, so Fn has components. You can't exactly see them because this is pretty tiny, but Fn has a vertical component pointing straight up and a horizontal component pointing straight to the center of the cone. Now, because this vertical component of Fn and Fg are the only forces acting in the y direction on the car, I mean, of course the car is not going to be accelerating up or down the cone in this particular problem, then those two forces have to equal each other because, again, they're the only ones acting in the y direction. So Fn y equals Fg. Now, what do we know? How do we know what Fn y is? Well, the geometry of the cone dictates that this angle is the same as this angle in the center of the triangle. Again, it's really tiny, but that angle right here towards the outside of the cone is the same as this angle of the half angle of the cone. And so to find that vertical component of Fn, we just do Fn sine theta like that, and again, set it equal to Fg, because they have to be the same, because the car is not accelerating up or down the cone. And then, of course, Fg equals mg, like that, and so you can just divide both sides by sine theta to get mg over sine theta equals Fn. Part C, derive an expression for the centripetal force. Okay, so centripetal force is the net force that is pointing in the center of the circular motion of the object. The only force that's doing that in this diagram is the horizontal component of Fn here, which is represented by the arrow of AC, again pointing towards the center. And so since, again, the angle is right here, then that would be Fn cosine theta. Now, we already know that Fn equals mg over sine theta, and so we can just make that substitution. So Fc equals mg sine theta times cosine theta. Cosine over sine equals cotangent, and so Fc equals mg cotangent theta. Part D, I have an expression for V in terms of the given quantities and any fundamental constants. Okay, so what is centripetal force? mv squared over r, right? Well, what is our r? Now, if you look again at this little cone here, we see that r would be this horizontal space between the center of the cone and the edge of the cone, like that. And we know that this part of the triangle here is h, as labeled in the diagram. And so what we can pull from that relationship, since we know the angle, is that tangent theta equals opposite over adjacent. So r over h, like that. Solve for r equals h tangent theta, like that. Substitute that in, so mv squared over h tangent theta. what else do we know about FC? It equals mg cotangent theta. And so we set those equal as well. Bring this down here. The m's cancel, so we're left with this. V squared over h tangent theta, h tangent theta equals g cotangent theta. Multiply both sides by h tangent theta. Square root the whole thing. Now, tangent can be rewritten as sine over cosine and cotangent can be rewritten as cosine over sine. Those cancel, and so they just leave 1. Therefore, V equals the square root of G times H. All right, before we start part E, I just like to draw out the cone real quick, just to analyze the angles and explain why we're going to be making the calculations we'll be making. Extend that line up here. This angle will be theta. The car will be around here. FG, FN, of course FN will have components like that. So far, these are the only forces acting on the car before we introduce friction. Now, if we extend this line of that bottom triangle, we get a 90-degree angle here, and of course we get a right angle here as well on both of the triangles. Now, whatever this angle is, we'll call it phi. Whatever that angle of the triangle is, that plus theta has to equal 90, because every angle in a triangle equals 180, and if this is 90, then the remaining two angles have to add up to 90 as well. So theta plus phi equals 90. Now, what else do we know? Well, this angle here, and combined with this little angle of the top triangle here, make a 90-degree angle, because the inside surface of the cone is directly perpendicular to the line of FN, and so they will form a right angle, and so phi plus this inner angle equals 90 as well. Well, what is that inner angle then? It has to be theta, and so this angle is also theta, like that. That will help us in our next calculations. Part E, derive the function for maximum speed in terms of r, g, mu s, and theta. Okay, so since this car is going at its max speed, its tendency is to go up this ramp. We'll take it like a bank curve. It's basically a bank curve. And on a bank curve, a car's tendency when it's going faster is to go up the ramp. Obviously, we don't want this thing to slip out of the cone, and so static friction, Fs, will be pointing down the slope like that. Call that Fs. Because, again, the tendency when you're speeding up on a bank curve is to go up the ramp. So Fs will point downward. Now, in order to find the function for max speed, we can use centripetal force, mv max squared over r. And we will also have to analyze the forces in the y direction, which ultimately add up to 0. Now, starting with centripetal force. What is the definition of centripetal force? The net force pointing in the center of your circular motion. And so, in this case, that would be fs, which of course also has components, and fn here. This angle of fs will also be theta because it's literally the same as this bottom triangle, oriented the same way, so this angle will also be theta. Again, net force pointing in the center, and both of those forces pointing in the center would be the horizontal component of Fn and the horizontal component of Fs. So we set that equal to Fn cosine theta plus Fs sine theta, like that. Now, as for the forces in the y direction, they all equal 0, and the only one pointing up in this case is Fn. So we'll put that one first, and then well, Fn sine theta, minus Fs cosine theta, because the vertical component of Fs here is adjacent to theta. And then we're going to set that equal to Fg. There's a reason for that. There's a reason for that. Because this is Fs, we can factor that out into mu s Fn, and then factor out the Fn. So like that. And then we'll just say Fg is mg, like so. And then divide both sides by this. Like that. Now, we can do the same thing over here. Again, Fs is the same thing as mu s Fn, so we can factor out Fn from both terms. Now we have Fn over here and we have Fn over here, so we make this substitution. Like that. Now we can cancel out the m, and might as well just multiply both sides by r at this point. And then square root both sides. And that is our equation for Vmax. Part F, derive the equation for Vmin. Now, in this case, since the car is going at its minimum speed, then Fs will have the tendency of pointing up the slope because we don't want the car to slip down off into the bottom of the cone. And so in that case, this particular case, Fs will point up like that. Still has components. Vertical pointing up, horizontal pointing right. Call this Fs. And again, this will be theta. Now, we basically do the same thing we did here. So mv min squared over r equals, this time we're subtracting the horizontal component of Fs from Fn because it's pointing away from the center. So Fn cosine theta minus Fs sine theta. And then we'll just little divider here. And then again, net force in the y direction is 0. And so we analyze those forces again. Fn sine theta. And Fs is pointing up as well, so we add that. Fs cosine theta equals, just go ahead and put mg there. And then again, we can factor out Fn. Divide both sides by this. Like that. Factor out Fn over here as well. Make the substitution. M's cancel. Multiply both sides by r. Almost ran out of room. New paper. This was what we had so far. We multiplied both sides by r. Plus mu s cosine theta, like that. Square root both sides. Like that. That is our equation for Vmin. Now, part F, part G, part G, part G. Part G, prove that the net force is given by the function, that thing. All right, so what we can do is borrow from our centripetal force function here. Why? Because pretty much the only net force acting on this car here is our centripetal force. All the y forces cancel out. They equal 0. It's not moving up or down the cone, and so the only net force acting on this object will be the centripetal force. And we will be using this particular version because it has a minus on the bottom and a plus on the top, and that matches our desired form here. And so we can say for part G, F net will equal F centripetal, which equals mv max squared over r, which, if you recall, equals mg cosine theta plus mu s sine theta over sine theta minus mu s cosine theta, like that. Now, what we can do to further make it in the desired form is factor out a sign on the bottom of the fraction here. That'll just be 1 minus mu s, and then whatever this becomes, multiplied by sine, and it has to equal cosine. And so obviously that would be cosine over sine, and that is cotangent. So that would be cotangent in there, because again, multiply that by sine, cotangent is cosine over sine, and so the sines would cancel out, and you would get cosine. Now, because all of these terms are being multiplied on both sides of the fraction, you can divide these terms on the top here by the sign on the bottom here. So if you do that, you get cosine over sine, which is again cotangent. And then these signs will cancel out. So this becomes simply mu s. And then we get 1 minus mu s cotangent theta. And then if you want the exact form, then you'll put all of that in parentheses. 1 minus mu s cotangent theta. And then just take the mg out like that.